we were writing yesterday because we didn't really finish. We didn't get to the point where we really actually finished it up. We only just barely threw it in there. We threw in some rendering code. They were saying there was an off by one error with the debug time marker. I'm not sure exactly what they meant by that, actually, on the chat. If they want to go ahead and point out exactly what it actually is, then we can go ahead and look at it explicitly. But I'll take a quick look just to see if I see what they were talking about. We have debug time marker here. We advance it. I don't see an off by one error in the recording of it. It looks like it's going to record one each time. So that's good. Basically, we go in here. We use whatever the current value of debug time marker index is. We increment it by 1, which is fine in the case where we hit the array. There we go. That's what we were looking for. This should actually be like that. That actually needs to be checking for whether we hit the actual end of the array. So that was a bug. Thank you for that. That is, again, one of those nasty little things. I don't usually make mistakes like that. I have to think that probably it is. I will admit, my programming does degrade when I have to talk and explain stuff as we go. And I think it takes up part of my brain, and it's a little harder for me to write bug-free code, which at the end of the day is okay, because I suspect a lot of people watching this stream are beginner C programmers or intermediate C programmers, perhaps, and so possibly it's better for me to have to debug more stuff just so we can go through it. So let's see there. That would lead to a gap once in a while, but we weren't seeing too many gaps before. So it's looking pretty stable here anyway. This is roughly what we were expecting to see before, so we're good. Yeah, so that is all good for now. Basically, what we need to do today is just decide how we're going to handle what decisions we're going to make based on the audio latency. So I'm going to go to the diagram for a minute and just talk about what we basically found yesterday. I should probably double mention, I guess, perhaps what that bug was, just in case people weren't clear. So before, I accidentally had typed that whenever the debug time marker index is greater than the array count. And basically what happens is, remember, these are zero-based arrays. So if I have an array, so if I've got debug time markers and I refer to the 0th element, it gets translated down to assembly relatively directly. Basically what this means is I'm going to take the pointer to the beginning of the array, which is debug time markers, and I'm going to add 0 to it, right? So what that means is the first one is actually 0. And the last one is actually whatever the count is minus 1, right? Because if we actually added all the count to it, we would be past the last one. We'd be pointing to one past the last one. We'd be actually pointing to one byte after the very last byte that was reserved for this array. What that means is that when we get to the end, we're actually at array count when we get to the end. I don't really need this greater than here. It's not really necessary. Really what we're talking about is when it's equal to array count. That's just kind of being paranoid and saying, well, if someone came in here and mucked with this value in some really bad way. But of course, we'd still have a bug even if that happened. So really we can do this. And what we probably should do is say this. We should probably say, let's assert that we're never going to access outside that array here, just so we can double check and make sure that we don't. So that's really all we're talking about. Nothing really too bizarre. But anyway, so that was just a stupid bug, and now it is fixed. And we can take a look a little bit more. Okay. So I'm going to Go ahead and open up the infamous Microsoft Paint, Paint Program of Champions. And we're going to talk a little bit about what we learned yesterday, much to our chagrin, I should say. So, we decided basically to start off with trying to hit 30 frames a second, right? And 30 frames a second translates into, right, you've got 1,000 milliseconds per frame in one frame, right? That makes sense. And so if we're doing 30 frames per second, 30 frames per second, right? Basically what we're expecting here is if we actually want to know how many milliseconds we're actually going to have in every frame, we would divide by 30, right? And so what ends up happening is we're expecting to see about 33.3 milliseconds every frame. That's how long we expect this to take, 33.3 milliseconds, like that, if that makes sense. Unfortunately for us, what we end up with is we end up with a we have a sound card in the machine that's going to output our audio, and what we would like to be able to do is frame boundary. We're computing the next frame. So if we are in here, if we're somewhere in here, you know, basically we're showing some frame, and this is the next frame. Basically, we're computing a graphic, right? You know, we're computing a little graphic here. We're trying to compute something that we're going to show right at this boundary. So this is where we're going to start displaying this to the monitor. So we're computing it, you know, sometime in here, and we're going to try and show it here. So ideally, what we would like to do is also compute the sound that goes with this frame and have it line up exactly. That's what we would like to do. Unfortunately, what we found out is that the audio latency on this particular computer anyway, it obviously is going to vary when going through direct sound. And we don't know, it might be lower if we were to try X audio. We haven't tried that yet, but you know, we have no way of knowing until we actually try. Basically, the audio latency is on the order of 33 milliseconds itself. We took a look at the difference between what's called the play cursor and the write cursor in direct sound, and we found that basically we could expect somewhere around that 30 milliseconds of latency, which is our entire frame time, which means that assuming we're inside a frame and we're displaying something and we're computing the next one, we can't expect our audio to show up until somewhere like in here, basically. Somewhere that's like wherever we start writing it. If we write the audio here, we couldn't expect it reasonably to show up at the earliest until somewhere out here, which means there's no way for us to actually compute the audio that goes with a particular frame and actually have it show up on that frame. That's just, there's really nothing we can do about it. That's just the truth. So, we've got a couple options here, and I can tell you about what they are, but none of them are great. What we may have to do is just regress to a very basic sound loop and just accept the latency and accept that it's never going to be synchronized, or we can try to do something that is synchronized on a machine that's faster, and we'll just test it somewhere there. And I don't mean faster like CPU, I mean less audio latency. But basically, if you think about what happens inside of a frame, we do have some other options that we could try to pursue, and I'll just discuss what they are briefly, and it may lead to us changing the way we do audio in our platform layer just a little bit. So basically what happens is, if we break down the time, there's inside of a given frame, let's say we're taking this frame, and we want to kind of blow this out into what is actually happening inside the frame. So we're going to divide up this time. This is our 33 milliseconds. We're going to divide up this time into what we're actually doing, right? What we're actually trying to do. What we're going to do here is the first thing we're going to do that doesn't really take a lot of time is we're going to gather input, right? We're going to gather input, okay? So we're going to get the keyboard, we're going to get the mouse if we wanted it. We're not really using that in the game, but we may use it for debug purposes. We're going to get the keyboard, which we are using for game pads, that sort of stuff. We're then going to update the game, right? So that's this. We then have some amount of time that we have to do update the game and make a render list. So we have to update and like do render prep, basically, right? And you'll see what that is kind of as we go through. But we're going to update and do render prep in here, right? Then we're going to actually have to do rendering, which is the majority, especially in this type of game where our physics, we're not doing like a 3D game, So our full 3D physics and collision detection, that sort of stuff, would normally take more time. But since it's a 2D game, we'll probably be able to keep that code pretty optimal when we write, if we write it properly. So we're not expecting this to grow that huge. It'll be complex because I'd like to make it fairly complicated, but I don't know that it'll grow that huge. It might if we start doing some things like fluid effects and stuff like that. So we can't guarantee that, but chances are, especially during when we have the software renderer, this is going to be a huge amount of time. When we start using GPU, it might go down quite a bit because GPUs, especially if it's a fast GPU, will just romp through a 2D game. But you never know. We can run in 1920 by 1080 all the time, and at full multi-sample and stuff, and suck down more GPU time and stuff like that. So you never know. Point being, that takes a bunch of time. And then any time that's left over, we're just waiting, right? We're just going to wait until the flip, right? And then here we actually display the frame, right? And this can actually be pipelined to some degree. So depending on how deep the pipeline is, a pipeline is basically something where you're going to push more frames down, have frames be computed overlapped. So we could start right after we finish rendering this, or even if we were multi-threaded, we could start doing gather input and updating before we even do the rendering, right? There's a bunch of ways we could overlap this. But if we're just doing it synchronously on one processor, no overlap, then this is what that's going to look like, and then we flip, right? And certainly back in the old days, this is what it looked like because there weren't multi-core things, there wasn't a GPU, so you were just talking about this exact process: gather input, update, render, wait, flip, right? Now the question then is, where do we insert sound in all of this, right? The answer obviously would be, if we are trying to minimize our audio latency and hit this time right here, then if we have a 33 millisecond sound delay, if we have something that's close to the frame thing, then we'd actually have to start outputting the sound for the next frame. We'd have to output it like back here, right? Does that make sense? We'd actually have to output the sound before we even gathered the input for this frame, which means that it's sort of somewhat impossible for us to do. But if you think about what was actually happening, if we go ahead and tack on basically another frame to it and look at the same thing, so basically just copy what we just drew, over here, what was this period back here that was before the thing? Well, this was the wait period, right? And then before that was the rendering period, right? So actually, all the way back to almost the beginning of this other frame, like let's say this right here is only taking 10 milliseconds, and this right here was taking 23 milliseconds, right? So we divide the frame time up, and basically the gather input and that update step is maybe only 10 milliseconds, and then we spent a lot of time rendering and waiting, probably mostly rendering. Well, that means all the way back here, if we look at what the time was, right when we actually, after we did the update, where we could have known what the sound was going to be, right, for the next frame. If we go all the way back here and look at that, if we were to sort of output the sound right here on the previous frame, we could have been only one frame behind, right? If we did everything exactly right, we could have been only one frame behind. And furthermore, if we actually take this wait period, or if we take this render period and overlapped and started the update for the next frame here, right? So this is where the gather input happens. So we basically overlap the gather input and update for the next frame with the rendering of the previous frame. If we actually overlapped those on 2 cores, we could actually hit the constraint of being 40 milliseconds or something ahead of where we wanted to write that audio and actually get our audio synced. But there's a cost. The cost is now we have pushed input gathering back a little bit further. So we've introduced basically 23 milliseconds, somewhere around, at maximum, 23 milliseconds of input lag, right? That would be the cost. So if you think about that, is that a good trade? Probably not. For a game like this one's, audio sync is not that important because none of the gameplay really revolves around hitting a sound directly. We will probably have audio cues in the game that try to help the player understand what's going on, recharge times, whatever, enemy attacks, that sort of thing. So, audio is important in every game. I certainly don't want to suggest that it isn't, because it very much is. But how tightly the audio synced is as a priority versus how tightly the input is synced, in this game, I'm going to say that the input lag would be way worse if we did that. So I think we really want to push our gather input as far forwards as we can, and we don't want to introduce that extra lag. So, given that we don't really have any options, realistically, given that, for hitting our audio sync on a given frame, what I'm going to suggest is that I backpedal a little bit from what I was hoping to do, which is keep the audio and video synced to frames, and basically say, all right, we're going to fall back to a little bit stupider, right? And what we're going to do is just say, all right, we're computing our stuff, and somewhere in here, after the update and input has happened, somewhere in here, we're going to try to write the audio. And we're just going to accept the fact that it's not going to be on a frame boundary. It's going to be basically somewhere in the middle of next frame. And we're going to accept the fact that there's basically 15 milliseconds or so on this card of audio latency, and it's going to write right into the middle. We will lie to the game. So we will tell the game that it is outputting this frame's audio. So it doesn't the game doesn't have to try and account for that 15 milliseconds of lag. We won't complicate the game's code by forcing it to do that. But what we will do is we'll basically say, all right, you go ahead and it's unsynchronized, it's a bit sloppy, but it's better than the alternative, which is pushing it out to this frame and having one whole frame of lag, or buffering a whole frame ahead and introducing input lag. So what I'm going to try to do is basically write it, go change our audio code so that is what we do in the case where the audio latency is greater than what we think we can achieve. In the case where it was less, like let's say we look and the audio card's got like 5 milliseconds of latency. It's like awesome. Maybe we're on a console or something and we can get that. Then what we will do in that case is we will try to make it so that it is offset, and basically we will write the audio with some buffer so that the audio for a frame does line up with the frame. So basically we're going to have basically a conditional sort of output. There will basically be one path for latent and one path for non-latent audio. And they won't really be paths, they'll just be our computation about where we're trying to hit will basically be sort of thresholded. So when we look at that lag, assuming that it's more than the some conservative estimate about where we can update our audio. Let's say that we assume that we're going to be able to update our audio, 16 milliseconds into the frame or something halfway through. Then we're going to say, well, if that difference here, if the audio latency is 16 milliseconds or more, then we're basically going to have to just be writing as soon as we can. If it's less than that, let's push it up to that 16 milliseconds to try and keep it right about here. And we can even measure what our average update time is in here to try and keep that as close as possible, if that makes sense. So yeah, we can do a bunch of stuff like that to try. We'll try to do the best we can, and we'll go from there. So that's about all we've got. And I'm going to go ahead and do that. I think I mentioned on Twitter, for those of you who are following, I feel like today might be a long session. I'm going to go ahead and do this. It'll take us a little while to do because this kind of code is always very finicky, very error prone. You saw how many mistakes I already made in it, and we'll make more, I'm sure. So it's going to take us a while to kind of go through that. But if we finish that in a reasonable amount of time, I may double the length of this stream. And basically do 2 hours plus the Q&A instead of 1 hour plus the Q&A, because there's some other stuff that I might want to do, and I feel like it's a Friday. So basically what we're going to do is every time we take a look. Alrighty. So basically what we've got here is we have said that we're going to have frames of audio latency, and I'm basically going to get rid of that notion altogether. So I'm going to get rid of frames of audio latency. We've got a monitor refresh rate. We've got our game update hertz here, and basically what we're going to do eventually is change these into let's take a look at these. We've got our two to-dos here. What we want to do eventually is change those to run to query Windows for the refresh rate, which we think we can sort of do, and just assume 60 in the case where we don't get it. But anyway, so what we're going to do here is actually delete this to-do that says let's think about running non-frame context for audio latency. That is what I just said we will decide to do. And let's use the right cursor delta for the play cursor just to target audio latency. That is also what we are going to do. So basically what we're going to do is every time we take a look at our get current position, right? So we come in here and we take a look at get current position. The play cursor and the right cursor, the difference between those two things is sort of the minimum audio latency we could ever expect to have, right? The right cursor says where it's safe for us to write to right now. The play cursor says where the audio is playing as far as we know. So if we look at those two, the number of samples in between them is the lowest audio latency we can realistically expect to count on direct sound giving us in terms of what it's actually playing, right? So we've sort of got a value here, right? We've got a right. So that is our audio latency seconds. That is the best that we're ever going to be able to do. So looking at that value, basically what we want to say is when we do our computation of what to write, we're going to take a look at this audio latency seconds value. And our, in fact, bytes between cursor, this should be audio latency bytes, really, right? So audio latency bytes, and that basically is going to be right here. So what I'm going to do is I'm just going to save these values for now. These are going to be actual values that go with our sound is valid thing. And maybe now might be a good time to start pulling these out, but I'm basically going to put those in there like that. Audio latency seconds. Where's audio latency seconds? There we go. So I'm going to compute those so that we can basically use those later when the sound is valid and we're computing where we're going to write to. Because you remember we kind of did a thing where we said that we wanted to make the sound be valid sort of the next time around. So here's our sound is valid. Again, bytes between cursors, audio latency bytes. There we go. All right. So basically, that's just going to leave those. Let's take a look here at where that happens. So that happens right here. Basically, what we were doing is we're computing where we want to generally end up in terms of where to write to. You know, where sort of in the running sample index we want to write to. So that is where our running sample index is. And I'd also say for math purposes, to do should running sample index be in bytes as well, because a lot of times we're mapping in and out of samples, but I wonder if that's really all that useful, because remember, there might be a little smarter, save some math and possibly reduce some errors. So that's all we're doing there. We're basically saying we're going to write, this is the last place we wrote to, and we now need to know, since we're going to lock from there, where is our target cursor, right? Where is that actually going to be at? And so before we were using the last play cursor, but now I think probably what we want to do is we want to basically say whatever the last write cursor was. So the last play cursor will actually keep the last write cursor as well. Let's see here. And this should make some people happy because they were nervous about the way I was doing it before. And you know, they're right to be nervous. It's always good to be nervous. I'm an experimenty kind of dude. I go in to code oftentimes. Oops, why did I delete that? I just wanted to add this one. I didn't want to delete the other one. I'm just going to save both of them here so we can take a look at both of them when we're doing our computation and printouts and so on. I like to go in and you can tell this code is very fluid, right? I'm just kind of hacking this stuff in here as I experiment around with it. And then you'll notice I've also never decided to pull this code out and tried to clean it up into a little encapsulated thing. And the reason for that is it's just not right yet. Like, we're playing with it. I'm not happy with it. I tend not to pull stuff out until I'm happy with how it works. And that is what's going on here, right? I'm just basically in there mucking with the code, trying to see what seems like a good way to have it work. And that's a very intentional. That's a very specific way that I tend to program, and I think it's a good way to program. Basically, I think that it's important not to try to make good, clean, readable, lovely code right away, because you burn a lot of time when you're in this state like we are now, where we're kind of pushing things around, where things are kind of fungible, and we're trying to massage them into a place that we're happy with it. We don't know very much about the hardware. We learned a lot about the hardware yesterday, all that sort of stuff. And so we're kind of pushing towards that point, and while we're in that state, I like to kind of keep things pretty, because you don't want to introduce bugs by how horrible it is. So we want to try and keep it a little bit cleaner, but, you know, we do what we can. Plus, I gotta admit, I can cheat a little bit, because on this stream, there are so many people who watch this program. I get kind of lucky. They catch errors for me, too. So I get a bonus. It's almost like I've got a pair programmer with me programming all the time, catching stupid mistakes that I make. That's kind of awesome. You gotta admit, there's some fringe benefits to doing this stream to me. It's actually kind of pays off a little bit. Just in terms of extra eyes on the problem. And you would be surprised how much that helps, because when you're programming, you miss stuff all the time, and having people who are just doing nothing but taking a look at your code and going, hey, wait a minute, does that work? And then going, he missed something, is pretty great. It's like having a whole suite of pair programmers standing behind you, just like catching problems. All right, so anyway, we've got those values now. So what we need to do is we need to think about when we're going to do our computation of where we want to write to. Basically, we know what our audio latency is. We know what the write cursor was, right? And so really all we have to determine is how much past the write cursor we actually want to write in terms of the sample count. So basically what's going to happen here, going back to the diagram, is we're in a situation where we've just flipped, right? We just flipped, and when we did the flip, we're at this point in time. In fact, you know, I can show you where we are in the code when this happens, right? We did our sleep, and by the way, that reminds me, I wanted to change this to this is not really supposed to stay in here. So log miss here. So this should actually not be an assertion, because this will happen. I don't like assertions for things that actually we know are going to happen. So we need to log a miss there. It's not here. Okay, sorry about that. Just needed, because I don't ever like asserting things that are actually going to happen. That's fine. I assert things that are going to happen when I'm testing code, but I don't like to leave those in there. We did our flip, Win32 display buffer window, and then we asked what the current position was. So basically, we did our flip here. We asked what the current position was, and right at the flip time. We asked where the play cursor is, and we kind of know on this machine it's going to be like right there, right? It's going to be pretty darn close to where here. The right cursor is actually going to be somewhere out in the, you know, the frame like here. This is where the right cursor is going to be, if that makes sense. Now it could really be anywhere. I mean, we don't know that. I'm just saying, you know, the play cursor is going to be somewhere behind where we are in theory, or close to. If we were really good, it'd be close to where we are. Or I guess you could even think of it as the play cursor might even be in front of us. So it's going to be somewhere right around where we are. Hopefully, if our audio sync isn't awful, it's going to be somewhere in here. Then we basically got the right cursor, and the right cursor could be anywhere out here, right? So we're hoping that the right cursor is somewhere kind of back in here if possible. We're hoping that we're not a whole frame ahead, but you know, whatever, it's going to be somewhere. So then what we have to determine, right, is from that right cursor, how much do we have to write ahead in order to make it so that the next time that we come back around, our audio latency hasn't caught up with us, right? So we're going to do a write, because we know that however far, you know, whatever our sync was, we're going to basically have to try to do roughly 33 milliseconds of writing, but we also need to account, and if these clocks were perfectly in sync, it would always be that 33 milliseconds of writing that we want after the right cursor. But we also have to figure, well, we've got this audio latency in here to account for. Now, I guess if you think about it, if the audio latency, this is the part that I was talking about with the two conditions, if we know that the audio latency is larger than the frame, so basically, I kind of need a better diagram here, because this stuff is kind of confusing, and I want to make sure that I've drawn it out just right. Okay. So let's take a look at that very first frame. All right. So we basically have our thing going on here. We're going to do our first frame is silent, basically, because we're not actually displaying anything. Our first frame is silent. We go to do the flip. This is the first time anything actually shows up on the screen. So we flip here, and then we ask, essentially we've got our sound buffer. Our sound buffer is here. This is our sound buffer right here. We ask where things are, and we find out that the play cursor is here. We find out that the right cursor is somewhere around here. So there's the play cursor and the right cursor. We figured this out at this particular flip, right? So that's where that is. Now, basically what we have to do is we have to start writing to here. This is where we're actually going to write. And so how much sound are we actually going to want to write? Well, it seems like we just want to write, at that point, we definitely would just want to write 1 frame's worth, because we know that this is already accounted for. So the play cursor is going to have to go the distance of the audio latency, which is our actual latency, right? It's going to have to go the distance of our audio latency and then start playing, and it's got a full 33 milliseconds to go, right? So that's totally what we want. And then this is just our 30 milliseconds of audio latency that there's really not much we can do anything about. Now, if we wanted to, then this is where it gets even hairier, right? You could imagine us actually waiting on that. We could, or doing that guess right about here, the first time out. We could imagine doing that guess right about here, and that would reduce our initial audio latency, right? If we asked here instead of at the flip. So what we could consider doing is saying, well, Yeah, let's time. So there's however much time between when we ask and when we expect to do the flip, right? That's going to be the elapsed time here, right? And the total time here of the frame, the total frame time. It's going to be the difference between those. It's going to be total minus elapsed is this time, right? So our total minus elapsed time is how much of the play cursor, right cursor thing we expect to eat up before we actually start playing, right? If that makes sense. Is less than this time. If this difference between the right cursor and the play cursor is less than this time, right? Then we are at that point. Then we are at the point where we need to delay and push it out further. So we're going to write after the right cursor, basically, right? And line it up like that. If it's later than, we're just going to write at the right cursor. And we're going to write that 33 milliseconds, right? So that's kind of complicated to think about. I'm complicating it even myself. In my head, I'm like, oh man, this is kind of complicated. So basically what we're doing here is whether that audio latency threshold is hit or not, we're going to have to do a different sort of thing. We're either going to have to intentionally sort of push our audio out in the case where we have a super fast sound card, or we're going to have to just write directly to the audio right cursor. When we look at where the right cursor actually is, we're going to write 33 milliseconds out from it in the case where it is too latent, right? So thinking about this, I think even though it's very complicated to think about, it's a lot of mental gyrations here. I think all that means is what we should do is when we go to write to the audio, we look at where the right cursor is, we say that we need to be ahead of that right cursor by the frame time. So we're going to write 1 frame's worth of audio past the right cursor. But in the case where the right cursor is actually far enough ahead that we don't expect to get there in time, we write that much less audio, right? So basically, if we go ahead and we query these things, and the right cursor is actually inside our frame boundary, it's actually earlier, right? The right cursor is somewhere inside before where the flip is. Then when we write the audio out, instead of writing the full 33 milliseconds, we could decide essentially to kind of push that out a little. How would that work exactly? The first time through, we would add a little bit of time to it. See, the confusing thing is we always have to write from where we left off. So the next time, I'm going to have to actually do this out just to make sure that we're doing, I'm going to actually do 2 frames, right? So the first one I'm going to do, I'm going to actually work out the cases 100%, just so I have both a good explanation and in my head a good way. So let's do first, this is audio low latency. So very low latency audio happening here. Something that's going to be extremely low audio latency on the sound card. So we ask here, this is our ask, right? So what we would want to do there is we'd want to move the right cursor forward on that first frame so that it lines up with this. So we're actually going to start our write here, and we're going to write just 1 frame of audio, right? That's all we're going to write, is 1 frame of audio. So that's what would happen here. We then ask again here, right? And we assume the audio latency is still very low, so we would get the fact that the right cursor is here, and we would be here writing to it, to this frame here, and we would want to write 1 more frame. So in this case, we would basically always just be writing just the 33 milliseconds, and we would never want to write anything else, right? But there's the audio clock problem where we want to make sure that we're not going to just constantly fill the buffer. Like, let's say we were slightly off, so we were always slightly writing too many bytes because our wall clock and the audio clock diverged. The audio clock was a little slower or something like that. That's the part that makes things really complicated. So we can't always write exactly 33 milliseconds. We have to write 33 milliseconds adjusted by however much the clock consumed. So what we need to see is how far did the right cursor move between those 2 times on average, right? So what we're going to do is say the average, instead of saying 33 milliseconds, we're going to say whatever the average right cursor movement was over, some number of frames, right? So we're basically going to say however much we think 33 milliseconds is in audio clock time, that's how far we would write ahead, right? So hopefully that makes some sense. So when we look at the right cursor, we'd say if it's going to be within here, we'll actually push it out to where we think it should be, and then we'd always write that average every time. That's what we would want to have happen. So basically, just to summarize what would happen here, we're going to, if we're inside frame for the right cursor, then we always write the average right cursor motion amount, right? So that's what we would do here. And I think that gives us the least audio latency versus the frame, because basically the sound would show up early if we just wrote to the right cursor, and we don't actually want that. So we basically want to wait. We want to do on that first one, we want to try to line them up. And then from then on, we always try to want to line them up again. Now, could we do this in a better way? Is there some way to look at the right cursor and do it without having to track that average? Because that would be nice if it was just a more stable computation, if that makes sense. How would we do that? So if we wake up here, and we basically find out that the right cursor, the difference between the right cursor and the play cursor is so we would expect the play cursor to be here in all, if we're assuming low latency we expect the play cursor to here. We find out that the right cursor is here, so we know the delta between these two is that, and we can sort of say, well, all right, in that case, how far do we want to write? Well, we want to write from the right cursor forwards to our sample index. We're assuming that the sample index fell on a frame boundary. Gosh, can you even do that computation? How would we do this computation using only the right cursor and the play cursor? Because they're the things that are in that clock space. Is there a way to do that? Yeah, I can't think of it. To be honest with you, I can't think of it. We know how far forward the right cursor, we know how far forward our estimated number of samples per frame is, but we don't really know, we don't really know anything else. That's something to think about. I don't know if anyone out there on the stream can think of a better way to do this. It seems pretty tricky to me to do anything other than just track that average, right? To track, you can see what I'm having trouble figuring out if there's a way to do. Basically, this is a wall clock thing that we're doing here. We're using query performance counter, but the audio clock may not be perfectly synced with the wall clock. It may be like a sampler or two off or something, who knows. Estimate where the write cursor would be, and I can basically say, okay, I'm going to make sure that we write at least past where that write cursor is, at least one frame past it. I guess maybe that's the way to do it. Okay. How about this? Here's a proposal. Here's a proposal for you. Tell me how the stream likes this. Let's say we do a thing where we wake up, we ask where the write cursor is, we forecast forward where we think it will be, right, basically. We say, all right, we have a wall clock estimate for where we think the write cursor will be. We push that forwards. We then say we want to write at least up to the next frame boundary from there, right? And that is the sample index that we write to. So it's always based off this. So in the case where the write cursor, and we do that only when the write cursor is behind, basically, right? Okay, I like that. We basically say round up to frame boundary from where the write cursor is projected, because that basically gives us the thing that we wanted, which is we always just fill the next frame and we're synced. We're synced to it properly at that point if the write cursor always is kind of behind. I like that. I like that a lot. That is feeling much better to me. I think we're getting there, people. Does anyone else love this stuff? That's the weird thing about it, too. I feel like there's probably a lot of people watching. God, there's just so much finicky stuff in here. But it's just like, there's something so satisfying about banging your head against something for a little while and then making a little breakthrough. It's kind of like playing a great puzzle game, right? It's like, it was confusing. It was confusing, right? And then you start to see little sort of breakthroughs there. And we're getting much better than we would have had if we just threw audio out the sound card. If you just throw audio out the sound card, you have no idea how it's synced. So even if someone makes a really low latency sound card and gives you this great hardware, your game just threw it all away. So you weren't synced at all. Your audio was early instead of late. But if we actually take the time to work this out just this one time, we then have an audio layer that can actually respond to that and be pretty cool. So I think we're making good progress here. And this, I don't know, this is what I like about programming. And then you get to write that great article someday, right? That's like how to do audio output right, and everyone can benefit from it, right? So I feel like it's good. It's just good to work this out. So I feel like that's it. I'm gonna redraw this here and make sure that I think that it's good. So we've got two cases. This is going to be the low latency case, and then we'll work out what the high latency case is in a second. Okay. So basically what happens is we wake up, we need to write audio. So this is our wake up. We find out where the right cursor is. We find out that the right cursor is basically less, we figure that it's inside the frame boundary, right? So the right cursor is inside the frame. That means that we will be able to actually be audio synced. We know that on this, we have a card that is low latency enough that we will be audio synced. So that's a card that had like 10 milliseconds of audio latency, 5 milliseconds of audio latency, some kind of pro-grade audio stuff coming down the pipe here. That's what we got. Maybe you're running on an ASIO driver. It's professional grade. Who knows? Or you're on a console and things are direct. So basically what we do in that case, what we do in any case, is first we project the right cursor forwards. So we take the right cursor, right? We take the right cursor plus frames, the frame samples, however many frame samples we want. If that makes sense. So we take the right cursor plus the number of samples per frame. We look at where that is. It's here. The next frame, the next expected frame boundary, right? So wherever that's going to be in time, next frame boundary in time. That's where we write to. So we write up to here, right? We come there and we then say, all right, we woke up here. We asked where the right cursor is. It's like here, roughly where we thought it was going to be. We project it forwards. We truncate up. We look upwards. We say that's where it has to be. We write forwards, right? So this is basically what we are trying to do. Okay. Now let's take a look at the case where we have a high latency card. So we wake up here, and here's our frames again, same frames. We wake up here. This is where we wake, right? Same time, because we're basically assuming that the game updates sort of not based on the sound card latency. So we sort of, waking up is a bad term. It sounds like we're sleeping. We get finished with the stuff here. We look at where we need to write our audio. We find out that the right cursor is actually going to be, out here somewhere, right? Excuse me. Okay. The right cursor is going to be out here somewhere. So we're like, yikes. Basically what that means is that where we need to write to is going to actually be just up to the next frame boundary at all. Is that correct? If the right cursor's there, then the next time we wake would be here. No. So basically it's the exact same. The code is still totally exactly right. The only difference is when we write up here, we could choose not to round up to the next frame boundary. We could choose just to add a different amount in here. So we could add however much we think our audio latency safety margin would be, basically, is what we could do. So we could do this right here. The target is rounded up to the next frame in this case. In the other one, we do the same thing. We do the WC plus frame samples, but instead now the target is just that. The target is that plus a safety margin, right? So we won't round up to the next frame. We'll just have a little safety margin, whatever we think we can get away with there, the lowest thing we think we could get away with in terms of our safety margin. And the safety margin would basically be, it's basically going to probably be just a few samples. I mean, it's because basically we're writing right where the right cursor tells us to be at that point. So the safety margin could be as little as like 1 millisecond or something, right? I think that would probably be fine. It's however much we think there might be variability in this, if that makes sense. So that safety margin can actually be quite a bit less than the delta that we were pushing up, right? So these are the two things here. So now the only thing we have to deal with is at startup, we don't actually know the concept of where the right cursor is not particularly understandable, right? If that makes sense, because we don't actually know where the right cursor is inside our frame, inside our kind of concept of a frame, if that makes sense. Like saying where the right cursor is versus it. I guess we do. It's just the play cursor is where we are now, right? The play cursor is where we are now, and the right cursor is where we will be. That's like as good as we can sort of do at that first initial startup. Does that make sense? I think that makes sense. So basically, we look at the delta between the right cursor and the play cursor. That's what we're going to get. Now, there's a problem. The thing with that as well, mapping that in there, that makes things even harder. So this seems like the right computation, but the one thing we have to remember is this play counter thing is very latent in terms of how often it updates. If you remember, basically that jump, let's take a look at that for a second here. I left that loop in for a very good reason. That jump, 0, 0, 0, the error of plus or minus 10 milliseconds, right? We don't actually know when we ask where this is. It could, well, I guess it's not plus or minus. In some sense, we know that it's plus or minus 5, I guess, technically, right? It's when we ask where this is, it could have been anywhere sort of in this zone, a 5 millisecond forwards, 5 milliseconds backwards in some sense. We don't know where it is because it updates so latently. So correlating our two buffers, we have up to 5 milliseconds of slop in there as well. That's just makes it even harder. So you see why this is so complicated. It really does make it pretty tricky for us to figure out how we could actually try, if we wanted to, how we could actually try to hit this thing. We look at where we are, we look at what the play cursor is, we just don't know. The play cursor is only updating every 10, so for all we know, the play cursor could be 10 milliseconds ahead or 5 milliseconds ahead or 5 milliseconds behind in terms of wall clock time. So we have to figure that every time we wake up, this is going to be this kind of nasty thing that shifts back and forth by 5 milliseconds. And 5 milliseconds is enough that we could end up, if we looked at where the right cursor is and we said, oh, it's inside, based on that estimate, what if that's wrong because of the 5 milliseconds? And it's going to jump forwards very soon thereafter. We could assume that it's always a minimum bound and do it that way. I'm trying to think if there's any downside to doing that. I assume it's always conservative, so I think we're probably still okay. Yeah. So I guess what we can do is just use the play cursor to determine where we are in the buffer, right? So basically, here's our sound buffer. We basically wake up, we say, where is the play cursor in the sound buffer, right? We mark where that is. That's where we are in the play cursor, right? At this time. We then know we have a certain amount of time left to go, so that we map into samples. We say, okay, here is where the frame boundary would be in samples, right? We say it's this many samples ahead of the play cursor. We look at the right cursor and we say, where is the right cursor relative to that, right? That's stable no matter what, I guess, because the right this many we play, right? So I guess what we can do is just use the play cursor to determine where we are in the buffer, right? So basically, here's our sound buffer. We basically wake up, we say, where is the play cursor in the sound buffer, right? We mark where that is. That's where we are in the play cursor, right? At this time. We then know we have a certain amount of time left to go, so that we map into samples. We say, okay, here is where the frame boundary would be in samples, right? We say it's this many samples ahead of the play cursor. We look at the right cursor and we say, where is the right cursor relative to that, right? That's stable no matter what, I guess, because, hey, it's a little late and whatever. We look at the right cursor. If the right cursor is behind that, then we're in this case. If the right cursor is ahead of that, then we're in the other case. I'm happy. I'm pretty happy with that. Basically, this is the same as a normal sound output loop, which would basically just be doing this, right? But we've now identified this other case where if we were given really low latency sound output, I think we now can actually literally hit our sound sync exactly. The more as the audio card converges to accurate, we will converge towards outputting sound that is right on that frame flip, like right on it, if that makes sense. I'm pretty happy about that. Maybe there's a mistake in our logic somewhere, but I'm pretty happy about what we just worked out. I wish we had a little thing that was like a little happiness flag. I feel like maybe the owl of shame, I don't know, maybe the owl of shame shouldn't be an owl of shame. Maybe we shouldn't reinforce our shame. Maybe we should reinforce our victories. I don't know, what do you think? Should it be an owl of victory or an owl of shame? We'll have to have a thread that's based. Of course, we can't hold it up yet because we don't know if this actually works, and we have to go actually do it because there may be a hole in our logic, but I like this. So what I'm going to do is I'm going to write a little comment here down at the sound output code that sort of says how this works, and when we extract this out and clean it up a little bit, we're basically going to leave that comment in there, just something that says how this works. So, because that was pretty important. It took us a while to figure out, so I'd like to kind of just notate it so that it's very clear. How sound output computation works. So, what we're going to say is we're going to say, in the case, so when we wake up to write audio, basically we will look and see what the play cursor position is, and we will forecast ahead where we think the play cursor to see if the write cursor is before that. If it is, we will write up to the next frame boundary from the write cursor, and then one frame further, which should give us basically exactly what we want. We will write up to the next, so one frame boundary, if it's before the frame boundary, we write up to the frame boundary, and then one frame further, giving us perfect audio sync in the case of a card that has low enough latency, right? So basically, we will write, we will write up to, I don't know how to say this right. So we will look to see if the write cursor is before that. If it is, I guess we'll say the target fill level, or whatever, the target fill position, is that frame boundary plus one frame, right? This gives us perfect audio sync in the case of a sound card that has low enough audio latency, right? If the write cursor is after the next frame boundary, then we assume we can never sync the audio perfectly. So we will write one frame's worth of audio plus a guard, plus some number of guard samples. So, 1 millisecond or something determined to be safe, right? So we can actually say this is whatever this is. Maybe it's half the frame time. It's whatever we think the variability, of our frame computation is, right? So we could set that all the way up to one whole frame ahead if we were nervous, but basically that's really all we need to do. And this is the same, basically what we need to say, if the write cursor is before that, it's really before that by our safe amount, right? So we basically have a safe amount. We should try to define this here. We will say we define a safety value that is the number of milliseconds or the number of samples we think our game update loop may vary by, right? And so however much that is. Let's say we assume that our game update can vary by, up to 2 milliseconds. let's say up to 2 milliseconds or something like this. So we'll say that if the game update varies by up to 2 milliseconds, then when we wake up for the audio, we look and see if play cursor is, we look to see if the write cursor is before that by the safety value, or by at least our safety value. And if it is, the target fill position is the frame boundary plus 1 frame. This gives us perfect audio sync in case the card is low enough latency. If the write cursor is after that safety margin, then we assume we can never sync the audio perfectly, so we'll write 1 frame's worth of audio plus some number of guard samples. So this, I think, plus the safety margins worth of guard samples. So basically this does exactly the thresholding that I set out to do initially, which is to say we always write 1 frame plus whatever the guard amount is in the case where we can't get audio sync to work right, because the card's too slow. If we magically were able to get some hardware that was fast enough, some really low latency hardware, then it would correctly do sort of the forward prediction to line it up with when we expect to flip, right? So that's, I'm pretty comfortable with that. How do you guys feel about that on the stream? How do we feel? I don't know. I don't know what you guys are doing out there exactly, but hopefully people are following that. But that's what we basically want to do. So what we do here is we take a look. We always have to basically write from so you know what, we're gonna always look at the, we don't have to save this, kind of nice, we don't have to save this stuff anymore for around the bend. We don't actually have to do that because we can actually the last write cursor, last play cursor thing, we don't actually have to save anymore, so that's kind of nice. We can go down here and basically get rid of that and say that from now on we're actually just going to use this stuff, and we don't have to save sound as valid as well. We're pretty much good to go on that as well. So sound is valid, can actually now be moved back to here. So sound is valid. If the sound isn't valid currently, we're going to assume that the... Did I actually accidentally delete the... Where is the running sample index update thing? I did. Yes, that was bad. What we're going to assume that it is, like I said before, is we've got 2 cases essentially. We've got these 2 cases to deal with. So basically we need to do an if here, and we need to figure out that target cursor in 2 different ways, right? And the target cursor now, I believe this stuff can be moved inside this loop. It can be made to be direct, like this. That is going to be our assumption, certainly, because, well, most audio cards probably are. If that makes sense. So we're going to see if the audio card is latent by saying, what did we say up here? We basically said if the write cursor, let's say, if the write cursor plus the expected sound bytes per frame, right? If the write cursor plus the expected sound bytes per frame basically is, okay, safe write cursor, let's call this. Sorry, not the expected write cursor plus the safety bytes, right? That's where we know that that's accounting sort of for the jitter. If the safe write cursor, right, plus that, we need to kind of know what this expected frame boundary byte is. So we basically say if the safe write cursor is less than the expected frame boundary byte, right? So this is the... All right, so we're going to take the expected frame boundary byte. That's going to be the play cursor plus however many bytes we expect to output on a particular frame. That's going to be some kind of a value that we compute up above that's pretty rote. It's just going to be however much the milliseconds is multiplied out by the sound thing. So basically, we've got that. We then check the safe right cursor is the right cursor. If it's behind the play cursor, which means it has wrapped, we're going to go ahead and normalize it so that it's ahead. We're not really normalize it, unwrap it so that it's always ahead of the play cursor so that we can do our computation properly. We take that safe right cursor, we assert that, that it's always going to be ahead of it because that was our goal. We then add in the safety bytes. That is where we say it could possibly be. We look to see if the audio card is latent. If the audio card is latent, by saying, is that safe right cursor going to be before, I guess we could kind of reverse this. Audio card is low latency, might be a bit better. So we'll say, if we can hit our thing, then we're gonna just reverse the sense of this test. So we're gonna say, if the audio card is low latency, then we will go ahead and compute that right there. So, okay, there we go. So that's how we determine this. That determines our latency. That's pretty good. We go through here. We say compute the target cursor by using just the frame boundary plus however many bytes we normally write per frame. When we are low latency, when we are high latency, we basically just use that plus the safety margin, and that's the target. We write to the target here. We map the target back into the buffer properly. And then we go ahead and do the bytes to write. So So there we go. There we go. I guess that's really modulo the bugs. That's really what we wanted to do. So our problem here, besides defining these things, our problem here is basically that we still need to tell the game how many samples it should output. And that's kind of, that basically gives us another audio latency problem, because where we want to actually do the write is right here. But the game unfortunately doesn't actually, hasn't actually updated. If we were to put this before, in order to tell the game how many samples to write, then we would have to, we wouldn't actually have an accurate read on where the play cursor was going to be when we needed to fill. So this is what we actually want to do for our fill, and we can assume basically that the sound buffer here, we basically need that sound buffer to basically always be enough that we wouldn't underflow it here. And so what we can do there, I guess, is just kind of have a thing which says we're generally going to write enough. We want to make sure this bytes to write value never underflows is basically the problem. And so what is the maximum value that bytes to write could possibly be? I don't actually know. I guess it could be the expected frame boundary byte plus the expected sound bytes per frame. So in this case, it could actually be pretty high. So if we move this before here, then we have another thing we've got to count on. You can see how tricky this basically is, right? So what we want to do is one thing we could do is we could then ask for the audio right here for the game and mix it on demand. And as long as we were able to keep that to within a millisecond or two, then that would be okay, potentially. But if it was going to be long, I don't know. So it's pretty tricky. It's pretty tricky. Should we do that? Should we not do that? Are we at risk there? I guess let's do it. I don't know. I'm feeling experimental today, so I say we just do it. So basically what's going to happen here is I'm going to say that we actually just go ahead and we get that sound straight out of here. So we go in here and we say, all right, what are we going to do? We're going to say internal void game get sound samples. So that's a call into the game, and we pass that everything except the graphics, and the input don't come in. So we pass that the game memory, and we pass that the sound buffer. And basically we will say that the game just does its mix down right there, right into the buffer. So basically the game no longer gets the sound buffer at all. And so the game has to give us sound buffers on demand like this. So in here we will simply say, let's go ahead, and as soon as we know how many bytes to write, we will actually do the write right here, and that has to be low latency, which is the thing that makes me nervous about it, obviously. That's the reason that I was kind of like, I don't know, this sounds dangerous. Well, like I said, sometimes you just got to do stuff, and then you got to fight through it, and see if there's something good on the other side. And sometimes there isn't, and it turned out to be bad. It was a mistake. And other times you come out with something really cool. And so sometimes you just got to do it and see. And so this is basically what we're doing here, is we're just kind of fighting through it and going, can we get something cool out the other end? And maybe there's a few more refinements left that we'll have insights into and see. But let's take a look here. So basically we'll get the sound samples right here, and we will output them right here. The other thing that we could do, which is pretty interesting if we wanted to, is we could write directly into the sound buffer here now if we wanted to, because we could change to passing a ring buffer to the game. We don't really, I don't think, want to do that at this point, but that's what we would do. So, all right, we went in here and we did that. We now have our explanation in here. I might actually move this explanation kind of inside. So basically, this is the explanation of what's happening in here. And that looks relatively clean to me at the moment. So we get the get gigabit sound samples. But I'm going to put a note here. I'm going to say, at the moment, this has to be a very fast function. It cannot be, let's say, more than a millisecond or so, right? So that's going to be important to keep our sound latency down. All right. So basically, we can always account for more of that by buffering up, and maybe we could measure things here. I could say, to do, Casey, reduce the pressure on this function's performance by measuring it or asking about it, etc. We could think about doing some stuff there to make that a little easier. But for now, let's actually say that that's the case. So compiling this, we now have to go through and fix our safety bytes is something that we will define kind of at the top when we first do our sound output setup. So and that is basically sort of like what this latency sample count is. So basically what we have to say there is how much do we think? Well, I think we can safely probably say that the variability in our game time is probably not going to be more than half the game time, right? So our safety bytes is probably something like the samples per second times the bytes per sample divided by the game update hertz, divided by 2. I think that's a pretty safe estimate. It's probably more like going to be more than like more of a quarter or a third, I'd say, because in general, I don't think we're going to have that much variability in how long the update takes. So basically, I think we could probably do this a little bit lower. So to do, basically, actually compute this variance and see what the lowest reasonable value is. That makes sense. Kind of get that in there, take a look at it. And then I just got to add that to this thing here. Let's see, dword safety bytes. There we go. Warning treat as error, game update and render. Right, so basically now we have to go in here and split this out. If you remember, we decided we changed the definition of these functions. So we got to go in here and basically split our functions into one that updates the sound and one that updates the game memory. So what we need to do here is we need to take this out, right, and get rid of that because we don't actually have that to do anymore. We're going to do this sound buffer output for the tone hertz. And basically what we need to do is we need to grab our game state. And so our game state is basically just, again, that permanent storage is how we access it. So let's go there, get that out from behind my head. Let's see, and we need to change this to be the proper function definition. It is this one now. So there we go, and go. There we go. Now, whew, man, we've got about 15 minutes before we would call this time for Q&A, probably. The bugs in there because maybe the next 20 minutes or so. Well, let's turn off the info. I am, at the very least, I am shocked that that still gives us a clean sound output, ladies and gentlemen. And it actually feels fairly low latency, so we didn't introduce any weird bugs, which is kind of crazy, to say the least. That is kind of crazy. What I want to do now is I also want to record with our markers. I want to record, I basically change what this records to record some additional stuff. This is where the play cursor and the write cursor were at the time of the actual. All right, so let's take a look at that. It'd be nice if we had labels and stuff, but let's take a look at that. So what do we have here? Basically, we're looking at that first one that we've got. And in fact, I guess while I do this, what I should do is bring this up in the debugger so we can see what the stuff is that we're actually looking at. All right, so what we're looking at here is we're looking at that first one is our actual play cursor and our output write cursor is that first row below the baseline. So basically that is the white thing is where the play cursor was when we were going to output, and the red line is where the write cursor was when we were going to output. Then the location that we computed was kind of out. You can see where the white line is and the red line. That's where we were going to output. And then the flip location is basically is the bottom white line, is where the play cursor was when we flipped. So you can see that's actually working exactly like we hoped it would. You can even see that's pretty good. Like, look at what we did there. Basically, you can kind of see that very bottom one. I kind of need a way to pause this display. Let's do a way, because I need a way to move my mouse cursor around. So let's add a way to pause this display. I'm going to just go ahead and full on just throw in a way to pause the display here. So let's do that. Let's have a pause. Let's have some crazy global pause thing. So basically, you know, something like this. If handmade internal. There we go. P, then global pause equals not global pause. And we'll just have, this is just a full-on debug pause function. We'll probably want to make a pretty good one of these eventually. Global pause. And basically what global pause will do is it will just stop us from actually ever running the update. So basically, while global running, we'll basically say inside here, when we do this sort of stuff, do we want to pause the input? I'm not sure, probably not. So what we'll basically do is say if global pause, like this, if not global pause, then we'll do all this stuff, right? We'll actually make all this stuff happen. Otherwise, we won't. So get window dimension, we won't do the blit. We won't do any of this. This is none of this is going to happen. Yeah, and so our basically we have to not do any of this stuff. None of this stuff is allowed to happen at all. So we can't really do input either for the most part. Yeah, looks like we can't really do anything if we wanted to actually have it be a full pause. So let's see here. Let's do that. Let's do this. So the Win32 process messages still has to get called, so we can unpause basically. But yeah, that's sort of going to be buggy. We'll have to do a better implementation of that going forwards. Okay. Of course, I also need to actually only toggle that global pause when the key actually goes down. Global pause. So we need to do if is down, then global pause. There we go. All right. So we run that, and now we can pause. So basically what we've got here is this is where the current let's just verify this, right? So the first thing that we drew below the baseline, which is this thing, the first thing that we drew was just our output play cursor position and our output right cursor position. So that was where when we woke up, when we asked where the things were, that's where they were, right? We then computed where we were going to write to, and we basically said, well, we're going to write to right here. Oh, sorry, no, that's not actually correct. Is that actually correct? What's the next thing? The output location. Okay, yeah. So the next thing is the output location. So then we said, okay, the output location is going to be right here, and we're going to write this much. Then, when we actually came time to page flip, we page flipped here, and this is where the right cursor was going to be, although that's not super relevant. So this is where we page flipped. So this is our audio latency. Our audio latency is between these two things. And you can see that that's actually much less than a frame now, which is good. That's what we wanted. And I suspect that sometimes it'll even be better than that, depending on how things work out for us. It could even be a little bit less. Not actually entirely certain, but yeah. So that's pretty good. I think that's not bad. I'm relatively happy with that, especially because we're actually doing things so that we could do lower latency if we wanted to. Yeah, that's not awful. I'm not unhappy with that. I'm relatively happy with that. I'm relatively happy with that. All right. So that should be good. Blood Dragon, I just glanced at the chat because it's time to go to the question. It says, initialize the global. Which global are you talking about? Global pause? This one? I thought we covered this. Global variables are initialized to 0 by default. And so pause is supposed to be false by default. But yeah. So someone was saying I missed an assertion for one of the things in here. Let's take a look. So output play cursor is asserted. Right. Did you try the audio without OBS? I did. It did not change. So OBS did not seem to affect the audio output, which is what I would have expected because it's going through the kernel mixer. So it should be pretty free for the kernel mixer to hand that audio to OBS after it's done sending it out. So it should. I wouldn't have expected OBS to in a well-working system. It shouldn't. So I'm assuming that it was fine, and it was. Yeah. There was a lot of thinking today. A lot of thinking. A lot of thinking on the stream. Is it inexpensive to query for the play cursor and the write cursor? Yeah, I think it's actually free. Is my thinking. The reason I say that is I don't think when you actually do that query, I don't think direct sound is actually doing any work. I think it's just returning you its internal values. And so I think what happens is direct sound updates those on its own time. So it's like occasionally resetting those values to whenever it pushes a new part of the buffer out or whatever, it updates those values. And then when you ask for them, I think you're just getting back whatever its values are at that time. So I don't actually think when you ask for it that it actually does any actual work. I could be wrong about that though. Audio seems to be the most complex part until now. Which will be the next more complicated thing? So I don't think we'll have anything as nearly as complicated as this audio output until we get to the rasterization till we get to rendering so when we do the renderer, if we just have like a rectangle, if we're just drawing like rectangles on the screen that are filled with bitmaps, so we're just moving like bitmaps around the screen, that's not that complicated. It's pretty easy to understand. When we get to, because I would like to be able to support in our software renderer the ability to like deform and stretch things, like skeletal animation sort of thing. When we write the rasterizer for that, that's going to be crazy complicated. They're not that hard to write if you kind of just know everything already, but even when you do, there's a ton of debugging to do, and if you've never done it before, it's pretty darn crazy complicated. And especially if we go and optimize it, which we will for SIMD, it's going to be tough. So what we just did is the toughest thing we're going to do for probably quite some time. And the other stuff we're going to do, like loading a bitmap, is going to be a breeze compared to that. Drawing the bitmap to the screen, a breeze. Understanding gamma correction and stuff like that, maybe a little more complicated. Alpha blending, a little more complicated than that, but still way easier than what we just did. But then when we get to fully deformable rendering, that'd be the thing. Audio asserts are a pain when debugging other things. Change to... Will this audio system be able to handle music and sound, or will the game have to mux the audio for us? Well, the idea is that sound and music are not different. So all the sound, music, and sound effects all come out through this channel. So basically, the operating system only needs to provide us with a way to output audio on the left and right channel, and then the game just pushes everything through those channels. So the music will just get mixed directly in there along with all the sound effects, because music and sound effects aren't actually different as far as the game is concerned in terms of what it has to do. How will you make sure that you don't have regressions in some parts that are not that easy to spot right away? Well, you can't. I mean, it's part of the answer. You put as much debug visualization stuff in as you can, and you put in as much assertions in as you can. But one of the big problems with games is they're entirely user input driven. They're entirely based on stuff that comes back from the operating system. So you can't really unit test them. Like, you can't do a lot of testing of components because usually the component style stuff is the stuff that's easy to debug. And it's the cross-system user input-based, like, complex states of system stuff that fails. And so you really can't do regression testing on most of the hardest part of the stuff to test. So that's unfortunate. I'm sorry if I'm being slow, but I still don't truly understand why exactly the audio is jumping. I'm not sure what you mean by jumping. It just seems like we should be able to handle it more simply. I've been trying to put it together through the stream, but I'm just kind of lost. So I'm not sure what you mean by jumping. Could you be more specific, Starchy Pancakes, about... Starchy Pancakes is a great name. Why the audio is jumping. By this question, I mean the original problem, not the current iteration. And so I guess just tell me what you mean by jumping and original problem, so that I can be just type it in and we'll answer it there. Why is the pitch of the sound changes after the game has been running a little while? So actually, I don't think that actually happens. That's the controller. So I believe that the controller right now, this controller has so this was change. What is going on there? No, that's weird. No, that's weird. That actually did change. What is going on there? I agree, that's a bit of a bug. Because I think our tone hertz should now be constant, right? So how are we actually getting a different sound output speed? Because that is even difficult for us to do. Because if we're always outputting it basically the exact same wave period, that seems pretty tricky. Now, to be fair, we're not actually accounting. One thing we could do is we could account for the fact that the sine loses its precision pretty quickly for our test value. So I should double check as well that that's not happening. Basically what happens is sine f, as this t sine goes up, I should guard against that happening. So, you know, the t sine value should basically just wrap every time it goes through 2 pi. Right? So basically, if t sine is greater than 2 pi, right? T sine can go back down by that amount. Basically, just normalizing it to its period, if that made sense. But I don't think that should have been it. Maybe it was. Yeah, that's so for what it's worth, that's way sooner than I would have thought. Sine would have lost its floating point precision, but looks like that's it. Looks like it literally loses precision that quickly. And I guess that makes sense. Those numbers, when you think about it, the sine wave is oscillating many times inside a second. So that number is getting really huge, and you just blow out. That's kind of cool how fast that happened if you think about it. Basically, we've got a floating point number here, right? And the floating point number, let's do it this way. I'm basically gonna see if I can kind of isolate roughly what when we hear that sound happen, I'm going to go ahead and break into the game at the point where that happens. So game output sound. This is pretty cool. I'm pretty psyched that that was actually it. I wouldn't have expected that, but I wanted to check, and it turns out that was it. So what I'm going to do is I'm going to drop a breakpoint into the game, basically, as soon as I hear that sound. As soon as I hear the sound change, if that makes sense. I'm going to drop a breakpoint right there. Okay, so I heard the sound change a little bit. So let's take a look. Let's see what T-sign is. So there we go. So basically what we have learned here is that when we get to 18,000, roughly 18,000, we have lost the precision necessary for the sign to still work properly. So I guess one question is, roughly where is that on the power of 2 spectrum, right? You know, where is that value? So if you think about what kind of power of 2 we need for that, that's somewhere around, you know, that's somewhere around 15 bits, let's say. Like if you, I don't know, where's the POW function? Scientific. What do we got here? Do we have square root? We do have square root. So let's see here. 2 to the 15th. Yeah. So that's somewhere around 2 to the 15th worth of bits in there. And then, so you figure if we have a 24-bit mantissa, right? So we have 24 bits worth of data in our sine, and we're using up, you know, something like 15 of them. That gives us 9 bits of precision in our sine wave left. Am I doing that right? Let's say something like that at that point. And so 9 bits of precision in the sound wave. What would that actually be? So 2 to the 9th is 512. Oh, all right. So you can kind of see what the problem is. So basically, we're down to 512 steps in our sine wave, and I guess that is enough that we can actually hear the problem. So yeah, we just ran out of precision. There weren't enough bits in the floating point value to actually make that work. 512 steps, well, times 2 pi. So yeah, I don't know. That's kind of surprising that it happened so soon, but I guess you kind of got to figure there just aren't that many bits in a floating point value. They lose precision pretty quickly. So there we go. I'm going to go ahead and turn the user input back on and see if we also have a problem with the controller, because I think that may be true as well. No, that sounds pretty good. So that's pretty good. So it looks like maybe it was only just losing sign precision. Again, this is just test code, so we don't really have to care about that, but it is nice to get it out of there because, I mean, since it's test code, we want it to be consistent, and maybe like if we'd had another bug in the sound layer, that could have been masking it, and we could have been thinking, oh, there's just a bug in, you know, in the controller output or whatever, and you know, it's just getting rid of bugs, even if it's in code that doesn't matter at all, is still good, because now at least we've reduced some variability there. Let's take a look. Sorry, I meant skipping. The original audio skipped when we moved the latency to be inside of 3 frames, I believe. Oh, okay. So the reason for that was basically just the way we were doing the computation was off of the play cursor. So we were kind of being a little too optimistic, right? Starchy pancakes, here is, I think, what you were asking. So basically what we were doing is we were looking at where the play cursor was. So we woke up and the play cursor is somewhere like here, right? Wherever it happens to be. And we were basically saying, okay, what we want to do is take the play cursor and take a look at where the next, I think what we were saying is something like, wherever the play cursor is, we're going to assume that the play cursor at the time of the flip, that's what we're doing. So the play cursor at the time of the flip, we were basically saying, let's go a frame ahead of that, right? Was what we wanted to do. And that's where we should actually write to. We should write to here in the buffer, right? So one frame ahead is what we would expect for it to be. And we're going to write one frame ahead of that, right? So it's basically 2 frames, right, is how much we would write ahead ideally. But we then knew that the right cursor actually was all the way out here when we started looking at it. So if the play cursor was even just a little bit off, then the right cursor would actually be here. And we would skip, right? Even if we were lined up properly. So what we had to do is write one full whole frame ahead of even the frame we were writing to ensure that by the time the play cursor got to the next one, the right cursor wasn't past the point that we had written to. Because if we'd written only to there, the right cursor would now be past it, and we'd get that gap. So it was really just because we wrote that code optimistically, assuming that the play cursor and the right cursor looked like that, but they actually look more like that, at least on this machine. Let's see, Clemens Baum says, it's more likely to be the accumulation of a small value onto a larger value that is a numerical problem. Mantis is not lining up. Okay, so basically what they were saying is that we couldn't actually increment it by, well, that's basically the same thing. I mean, those are 2 sides of the same coin. Basically, the fact that we can't add a small value to it is the same as saying there isn't precision in it to record the size of the value that we actually need for the most part. But yeah, I agree that maybe if you could do the math in a way that was a little more amenable to it, All right, so if we're going to do that, we already did part of what we need to do for that, right? We have asset slots for sounds. What we don't have at the moment, and we also have tags for sounds, right? What we don't have at the moment is actually any way to load a sound, right? We don't even have anything like that. And so when we have something like load bitmap work here, we have load bitmap, we basically want to make an exact copy of this conceptually, but instead of doing it with bitmaps, it would do it with audio. So instead of doing the work necessary to load a bitmap out, it would do the work necessary to load a piece of audio out, right? And so what we want here is something that, looks basically like exactly the same, something like this, where it does this, but for sounds, right? So here's sounds. Here's the ID value from them. We set the asset state of them and does exactly the same thing. We then begin a task for it. We get the task out, but instead we would do like a load sound work here, and then we would just fill out exactly the same stuff. Only it would be instead of a bitmap or something like this, it would be something else entirely, right? So yeah, that is what we would want to do, and I feel like that's really, that would really be it, right? So what we need to do is have a thing. We've got loaded bitmap. Let's take a look at the renderer there. Here's loaded bitmap. We've got loaded bitmap, and what we really need to do, I suppose, is make an equivalent for audio, right? And so we would need something like loaded bitmap for audio, right? We would need something like loaded sound, and that would probably be something that just told us what the sample count was, right? Like that, and it would be, something which, which was just like how many samples, and then the memory for the samples, right? Something like this. I feel like that's all we would really need, because all of our sound samples, all of our sounds would be in the same format, presumably. So there really wouldn't be much else that we would need to do. So yeah, so I feel like that would be basically it. Yeah, I'm trying to think if there's anything else. I also think we may be able to do some collapsing here of stuff. There's more stuff we'll be able to do a little bit later, but for now, I think it would be something like that. And so yeah, so as we do this stuff, we would want to have that work order be something like this, right? And this guy would just be, a loaded sound star, like so. And looking at it there, they're really so close. I feel like maybe we will end up collapsing these. I'm going to leave them as separate things at the moment, but I feel like they may end up being so close that we just collapse them down into one thing. It's really hard to know sometimes before you do something how different two code paths are going to be, but when they start to look much like compression-oriented programming, approach, you just want to look and go, oh, these two things are working exactly the same way. Maybe I can merge them together and make, less code. That's always a good thing. So, okay, if we do something like this where we have a load sound, we pass it the ID, we go ahead and do this stuff. What we would want to do now is we would want to, wait a minute, there should be a sound, this should be like sound ID, right? Sound ID. Do we have that yet? We've got bitmap ID, there's audio ID. I don't know, it shouldn't be audio, it should be sound ID, right? There we go. Sound ID, like so on. Okay. So when we load that in, that would all be good. And then we just need the actual function, like this guy here, which actually does the sound loading, right? So we need something that does like load sound work, right? Like so. And what this would do is this would, do the equivalent of what the bitmap thing does. It would say, all right, we have a sound info structure, presumably, which is exactly the same as the asset bitmap info kind of thing. So like this, so it's sound info. At the moment, it would probably also just be a file name, right? Asset sound info, sound infos, like so. And we want to grab out whichever one that is because that's the one that we would actually use. So there's our work ID value, right? Blah, blah, blah. We would then go ahead and say whatever that one is that we're loading here, the sound. We'd probably have a debug load wave file for something like this, right? We would grab out just the file name from the info. We'd do that, and then we would, well, that would be the end of it, right? So let's go ahead and see. We've got our debug load bitmap function, or at least I thought we did. Oh, right, it's in here now. We've got our debug load bitmap function, and so what we want to do now is do a version of that for wave files that's going to do exactly the same thing. So let's see if we can just start to bang a little bit of that out as well. So we want to do essentially the same thing here that we were doing before. If we want to make one of these, there we go. We want to basically do exactly the same thing. We want to do a debug read entire file. We want to see if we actually get anything back. If we do, then we want to take the contents and start to look at them as an actual wave file. Now, wave files are a little bit more difficult to read than BMP files, but not by much. I'll go ahead and bring up the docs here for it. WAV file format, right? And here we go. Let's see if we can get a reasonable documentation of them here. Let's see. So this will probably do. Let's see what we have here. Multimedia player. Let's see. Do we want all of that? Pages 56. Wave update. I don't know that we really want all of this stuff. This I guess looks like a pretty. Maybe we'll just use this web page. I don't know. Seems okay. Anyway, so the way that wave files work is there's this concept of a chunked file format. And these show up, I don't know if the first one of them, I doubt it was really the first. But there was a thing called the IFF format, right? And it was I think Electronic Arts made it. It was by Electronic Arts, and it was on the Amiga. And this is the first one that I ever remember seeing that worked this way. I suspect there were ones before it because it just seems like there probably would have been, but I just don't recall any of them. And basically the way that they work is they try to create a generic way of encoding hierarchical data, basically. So what they do is in the file now, remember exactly like a bitmap, this is just in the file, there's bytes in the file. What they do is they encode like an ID, and that ID is usually, in these cases, it's 4 bytes is the way these work. And the 4 bytes are mapped to actual ASCII characters typically. So there'll be things like WAVE or something will be the actual ID of the chunk. So it's not like 0, 1, 2 are the IDs. The IDs are actually often 4 different character values packed together. So this is some crazy, big, huge number if you looked at it as a 32-bit integer, because it's actually the 4 bytes of wave, right? So typically what they do is they have an ID of a chunk, and then they have a size. And what you would typically do is the way you write a file parser for one of these is you look to see what the ID is, and then you look to see what the size is. If you understand the type of ID that you see, so it's one of the ones in the set that your program understands, you then parse out, go start processing the bytes that are size amount of bytes in the file that come after that chunk. If you don't understand it, you just skip that section, right? Because you know how big it is because of the size, and you read the next section. And that section also has an ID and a size, right? Now, inside these, you can also have, if one of the definitions of the chunk is that it's got subchunks, then inside them you can have more little IDs and sizes, right, that have other stuff. So you can basically just imagine this sort of hierarchical structure that you can create with these things. It's not a particularly good way of doing a file format. I definitely don't recommend it. It's an old school way of doing things. You can almost think of it as like HTML and binary. Better than HTML because at least it's got sizes and can encode binary data in a sane way. But it is just a little bit janky, to say the least. Anyway, so if we go ahead and start to parse this, what we would need to do is start by taking so if I do that, right, now when I load any kind of WAV file that's doubled, it should do that. Okay. So So if I do that, right, now when I load any kind of WAV file that's doubled, it should unswizzle the left channel properly, but the right channel is going to be total garbage, right? So what I want to do is I just want to take a look at what the right channel actually ends up being, right? And I guess for now, I said I was going to leave it as a void, but I might change it to a unit 16 just for a second. So I guess, to be completely honest with you, I don't really know where we left things at the moment in terms of sound playing. We have game output sound. The moment is still being called. And I guess we actually are outputting something here, which is, I guess, this. T sign. We don't actually have game state T sign. Does that ever get incremented? Plus tau 32 wave period. Game state T sign. Tau 32. All right, so I guess we would just put this back in, right, for testing purposes. I don't know what else to do at the moment. So I'm going to go ahead and put that in just so we can see if our sound output is still working first with a sine wave before we do anything else. So here's our T sign, and I'll go ahead and run that and see if we have any sound. We do. All right, so that's all good. So if we want to play an actual sound wave now, that's, you know, if we were going to do game output sound for something else, I guess what I could do is just say, well, let's say we've got a loaded sound here called test sound, right? And I'm going to go into to the place where we loaded the sound there, load WAV, and I'm going to say that game state test sound equals that sound. So when we come in here, and was that, so I had that at the beginning, so that was actually loading the sound every frame, and apparently that was fine. That's kind of crazy. Anyway, so I'm going to put that in here. When we actually do this, this is just, you know, to test the debug loading. That'll go ahead and load it into test sound. And then what we can do, if we want to, is we can have this game output sound thing actually do something a little more useful, potentially. I don't actually know why I have a separate function called game output sound, but yeah, whatever. So if we actually get rid of this, I'm just going to say that that's not getting called anymore. If I actually just come in here and put, put this in here, I'm going to go ahead and say we're going to output to the sound buffer like so, and the sample value that we're going to output is just going to come from that debug sound that we loaded, right? So I'm going to say that the game state test sound, what do we call it? Samples, I think. We're going to say that sample 0, that first channel, I'm going to grab the sample index of that and put it into the buffer. Now, of course, we want the sound to continue playing over time, or test sample index, like this. So what I want to do is say, okay, you know, it's actually going to be the game state plus wherever we were in the sound plus the sample index. Then at the end, we'll go ahead and advance that by however many samples we actually retired, like so. And then all I want to do in here is say, oh, you know, I never want you to play more than whatever the sample count was, obviously, right? So whatever its sample count was, only play that many, right? So let's take a look. what did I do there? Game state sample, test sample index, right? Mod test sound dot sample count. Missing, you're right, I am. There we go. Or maybe not. What did I do? Game state, oh, sample value. That's what I wanted. And so that was actually correct. Sample out. Whoops, did I not copy the thing that actually figures out where we're writing in the buffer? Sample out, there it is. Okay. That does not sound particularly good. I'll give you that. So let me actually go through and step through here. So this is going to be our